Mr. Tarot. Okay, so in this lesson, we are going to be taking a look at the ratio test. There is a root test. We don't need to cover it. So we're going to be specifically looking at just the ratio test, and we're going to be done learning all of the types of convergence tests that we need to worry about for AP Calc BC. So we've learned a lot. What's the very first thing you should always do to determine if a series converges or diverges? Nth term test. If the limit of a sub n, if the limit as n approaches infinity of a sub n is not equal to 0, then your series is guaranteed to diverge. Please do not do a whole bunch of work determining that the series diverges when you could have just done an nth term test right off the bat. I have learned from experience. We have a geometric series. What are we looking for in a sub n for this to be, for something to be geometric? An R. That was nice and loud. Thank you very much. You may have an initial value a, but there is some kind of constant base that is raised to a power. If the absolute value of r is less than 1, then that series will converge. If the absolute value of r is equal to 1 or greater than 1, that series will diverge. And that series, not only will you know based on the absolute value of r being less than 1, but because of our formula from pre-calculus, which is that the infinite sum of a geometric series is a sub 0, a sub 1, whatever your first term is, divided by 1 minus r. That is the formula to find the infinite sum. What is the domain of a sequence? We just literally covered this.
All real positive integers.
Saying the word real is kind of like true, but is it real numbers or is it positive integers? It's just positive integers. Thank you. Now, we have some formulas, like we have a formula for a general term of a geometric sequence that we learned in pre-calc or relearned in pre-calc. And if you have a need or desire to change the limits of your summation notation, like if you want to make this notation kind of match more closely what we had last year when we learned geometric sequences and series, where the domain is positive integers, you could maybe say want to add one to the lower limit of the summation symbol. If you add one down here, you're going to have to subtract one to every n, every time that n appears in your a sub n notation. So, which is especially helpful when we start talking about Taylor series coming up, Taylor-Maclaurin series, or just trying to make your answer match some kind of solution guide. How do you know when you have a p-series? When your a sub n is
Power in the denominator.
a fixed power. It's 1 over n, right? And n is going to be your variable of your summation notation. But it's like 1 over n to a constant power of p. So your numerator is a constant. If it's something other than 1, you can move it out in front of your a sub n or just all the way out in front of your summation notation. And 1 over n to the p, if p is greater than 1, that p series is going to converge. And if p is equal to 1 or less than and greater than 0, then that p series is going to diverge. Of course, if you see that you have a sub n, a series notation where there's a negative 1 to an n or an n plus 1 or n minus 1 power, if you see a base of negative 1 inside your series notation, where you open the door for the sign of your terms in your series to be both positive and negative. And they can alternate in different patterns, but the most common one is plus negative, plus negative, plus negative. Then you're looking at an alternating series. So separate that negative 1 to a power and look at a sub n as being a term that's greater than or equal to 0. If a sub n plus 1 is less than or equal to a sub n, and the limit as n approaches infinity of a sub n is equal to 0, then that series is going to be convergent. With alternating series, we have a specific formula for the remainder where you're estimating the series, which, by the way, your geometric series and your telescoping series are going to be the only two types of series that you can exactly find the sum of the infinite sum or the series value. Everything else is either just these tests are determining whether this infinite sum exists. Maybe we don't necessarily know how to find it, but we know it exists because we have a convergence, a test that gives us convergence. With an alternating series test, or if you have an alternating series that you have determined converges, the absolute value of the series value, the infinite sum, the absolute value of the series value minus the partial sum is going to be equal to the absolute value of the remainder that you find, the difference between the infinite sum and the partial sum. The subscript of n is a partial sum. If you have a remainder based on the sum of 4 terms, then that is the difference between the sum of an infinite number of terms minus the sum of only 4 terms. And that remainder that you get is going to be less than or equal to a sub n plus 1, or your first neglected term, which probably still needs to have absolute values around that. So let's fix that. OK. When you have that alternating series, if the absolute value of n, so you're going to take the term that is in your summation notation, if you can take the absolute value of that and determine that the absolute value of your series converges, then your alternating series is going to be said to converge absolutely. If you can take the absolute value of n, get a new series that converges, then your original series, your original alternating series, absolutely converges. If you have a situation like your harmonic series where the alternating harmonic series, your alternating harmonic series is going to conditionally converge, where the given series, which is going to be alternating, like an alternating harmonic series, that converges based on the alternating series test, where a sub n plus 1 is less than or equal to a sub n, and the limit as n approaches infinity of a sub n is 0. But the absolute value of your alternating series, alternating harmonic series, is your harmonic series, which does diverge. The test for convergence that me personally is my least favorite, the one I'm going to avoid at all costs, is your direct comparison test. You have a series. If you can look at your series, which is only going to come with experience, and believe that it converges, then you're going to create a simpler series, which is going to be based on a b sub n term. And you're going to be looking to create a simple series that is easy to determine if it converges. And if your new series that converges, I'm pointing to b sub n. That's not, I don't have a series notation. That's just the b sub n term. But you show that b sub n is greater than or equal to a sub n, then you've created a simpler series that you can easily determine converges. And if each term of b sub n after a point is greater than or equal to a sub n, then the given series converges. If you look at your given series and you believe it to be something that is going to diverge, you're going to have to create a series that is easy to determine that it diverges, and then also show that each term of b sub n is going to be less than or equal to a sub n after a point. Then you can use that to prove that the given series diverges. Your limit comparison test, you're going to be doing a limit comparison test if your a sub n is like a rational function where it's a polynomial over polynomial, or maybe you have a polynomial over or under some kind of square root function that has an algebraic expression on the inside of it. Think of pre-calc when we talked about determining horizontal asymptotes of rational and irrational functions. You're going to focus on the highest power of the numerator and denominator to come up with an easy series, a series based off of b sub n that you know either converges or diverges. And then the limit as n approaches infinity of a sub n over b sub n, if that limit comes out to be a real value, then both your original series and the one you came up with are either going to both converge or diverge. And this is all just super cliff noted version, so I can fit all this up on the board at the same time. The only series that allows negative terms is your alternating series, where you alternate between being positive and negative. Your integral test, which we have learned can take a lot of work, but sometimes is really wonderful. If you can come up with a function f of x that is actually a proper function and agrees with a sub n every time you plug in a positive integer after a point, if you can come up with an f of x that is positive, continuous, and decreasing for x is greater than or equal to 1, you might need to, again, negate maybe the first few terms. X is not always going to start at 1, but that's the way the rule's written. and a sub n is equal to f of n, then either your given series and your improper integral based on f of x dx, they're either going to both converge or diverge. So if the improper integral gives you a positive real limit, then that improper integral is converging, thus your given series is going to converge. If you have a series where you see the denominator is factorable, then hopefully you can use some partial sums or partial fraction technique, excuse me, to create a difference of terms. Write out an expansion of s sub n, see a lot of things cancel out, and if the limit as n approaches infinity of your partial sum formula equals some real limit, then the given series that you had in the first place is going to be said to converge, and it will converge to the limit that you get from the limit as n approaches infinity of s sub n. And so the given series is going to exist, and that infinite sum will be the limit that you found from your partial sum formula. And then finally, the new material, the ratio test. Let the series, or let sigma starting at n equals 1 and going to infinity of a sub n, whenever you see the summation symbol with no lower and upper limit, you can assume it's implied to be a series. Let a series a sub n be a series with non-zero terms. The series will converge absolutely when the limit as n approaches infinity of a sub n plus 1 divided by a sub n is less than 1. Your series is going to diverge when the limit as n approaches infinity of a sub n plus 1 divided by a sub n is greater than 1 or goes to infinity. And your ratio test is going to be inconclusive when you go to do the limit as n approaches infinity of a sub n plus 1 divided by a sub n, and it comes out to be 1. All p-series, and I don't know why you would do a ratio test if you realize you have a p-series, because the p-series test is so simple. But your ratio test will always be inconclusive when your series is a p-series. And notice we are talking about absolute value. So the absolute value of a sub n is a p-series. You're going to be wanting to do a ratio test when you see that a sub n has variable exponents or factorials. So this is the last test for convergence that we are going to study. So in your homework, you're going to start seeing a collection of problems. We're going to focus on doing the new work, the new ratio test. But you'll have a big section in your homework that just throws out a bunch of series notes at you and say, determine their convergence. And you're going to have to determine which of these tests are your best choice. And that is only going to come through experience, which is why I'm kind of trying to summarize all of this for you at the same time. Give you some nice notes and also kind of like remind you of what you've seen. Yeah.
It's just too pretty.
Oh, thank you. That is one thing I have to do if I'm recording videos is the overhead does not work well. So let's take a look at example 1. We've got, what type of series is this? It's alternating. It's an alternating series. So we might be able to work out like an alternating series test to determine if this converges. But what's the strongest type of convergence when you have an alternating series? Absolute. So the series converges absolutely when the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n is less than 1. So we're going to look for that absolute convergence first. Plus, why not practice with something new? So we're going to see here that a sub n is going to be basically the absolute value of this. We're going to drop the negative 1 to the n power. A sub n is 3 to the power of n over n plus 1 factorial, thus creating an a sub n plus 1, which is 3 to the n plus 1 over n plus 1 factorial. So let's see what we get for a limit. We have the limit as n approaches infinity of the absolute value. Actually, let me keep the negative 1 to a power, even though arguably it's going to be going away with the absolute value. And we have negative 1 to the n plus 1. Probably going to do this one time for notes. negative 1 to the n plus 1 over 3 to the n plus 1 over n plus 1 is n plus 2, so over n plus 2 factorial, that is our a sub n plus 1 in the numerator, over a sub n. So over negative 1 to the n power times 3 to the n. So what would happen if you didn't write a sub n and a sub n plus 1, without the negative 1 to a power? You'll see that it cancels out anyway. Over n plus 1 factorial. When you start doing a bunch of these, you're not going to write a sub n plus 1 divided by a sub n. You're going to do a sub n plus 1 multiplied by the reciprocal of the denominator. So we're going to have the limit as n approaches infinity of, okay, let's go ahead and drop the negative 1 because it is an absolute value. So of 3 to the n plus 1 over n plus 2 factorial times n plus 1 factorial over 3 to the n, and again, taking the absolute value of that. By the way, this ratio test is going to come up to be really, really important in the next few sections, the last few sections of the chapter, as we go to determine the radius of convergence. So this will be something you do a lot as we finish up chapter 9. How many bases of 3 do we have in the numerator? N plus 1. How many bases of 3 do we have in the denominator? Just n of them. Now, if you want to see this, 3 to the n plus 1 is 3 to the n times 3, right? 3 to the first. When do you add exponents? When you multiply like bases. So your 3 to the n's are going to cancel. N plus 2 factorial is n plus 2 times, and then n plus 1 factorial. So that n plus 1 factorial is going to cancel, giving us the limit as n approaches infinity of the absolute value of what? 3 over n plus 2. And now we're going to let that n go to infinity, and we have 3 over infinity plus 2, which is basically approaching 3 over infinity, which is what? 0. Whoop, whoop. And what does it say over here? If the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n is less than 1, then the given series converges absolutely. So 0 is less than 1, therefore the given series converges absolutely by the ratio test. And that's how you do a ratio test. So let's try one more. The series where n starts at 0 and goes to infinity, or the summation where n starts at 0 and goes to infinity, of 7 to the n power over 3 to the n plus 1. So you're going to look at this, and the very first thing what should be the first thing we do with this? Yeah, really the first thing you should be doing is an nth term test. And we have the limit as n approaches infinity of 7 to the n over 3 to the n plus 1. Now, if you're doing this with an absolute proof, the numerator is a base of 7 and the denominator is a base of 3, and you're constantly multiplying by 7 versus constantly multiplying by a base of 3. So it's looking like this is not going to be equal to 0. But we actually have to prove this, and with L'Hopital's rule, it's going to be hard to prove this with L'Hopital's rule because the derivative with respect to x of a to the n, or a to the u, is going to be the natural log of a times a to the u prime. And so you're still going to have a base of a in the numerator. So I think it's pretty clear that this is not going to approach 0. But just for the purpose of maybe, well, I want to do another ratio test with you. And also, like, while this seems obvious, maybe it's a little bit hard to prove. And I'm sure I'm going to get comments to explain how easy it actually is, or just so obvious why you're going on. But let's run this through. So maybe I don't have the best example here. But let's go ahead and run this through a ratio test. Take a minute and try and determine that this thing actually does indeed diverge, I mean. Would this be a good candidate for a ratio test? When do you want to think about doing a ratio test? When you have variable exponents and or factorials. Yeah, so this would be an excellent candidate for ratio test. We got variable exponents. This is a good fit for the ratio test like we just said. So with that ratio test, we're going to do what, Mr.? The limit as n approaches infinity of the absolute value, which we don't need because this is all positive, but
7 to the power of n plus 1 divided by 3 to the n plus 1 plus 1.
good. And then that's getting divided by a sub n, but you're probably, did you multiply by the reciprocal? Good. So there is a division down here of another fraction, but we're going to bring that up and instead multiply by the reciprocal. So we have times
3 to the power of n plus 4
divided by what? 7 to the power of n. Okay, so then that, what cancels out? Yeah. In the denominator, we have n bases of 7, and in the numerator, we have n plus one more base of 7. So now we have the limit as n approaches infinity of 7 over 1 times 3 to the n plus 1 divided by 3 to the n plus 1 plus 1. Okay, so this is going to be equal to 7. We can bring this constant out. The limit as n approaches infinity of 7 is just going to be 7. And we have 7 times the limit as n approaches infinity of 3 to the n plus 1 divided by 3 to the n plus 1 plus 1. Okay, so we didn't quite have this situation in chapter 1, but when we were analyzing limits of fractions, and they were, in the beginning of the year, they were polynomials. We would take the highest degree in the denominator and divide that out. So if we had like an x squared in the numerator and x cubed in the denominator, we divided the numerator and denominator by x cubed. So if you really want to analyze this like perfectly accurately, what you would want to do, and do it almost like a proof, is you take that highest power in the denominator and divide that out. So we're going to multiply the numerator and denominator of this fraction by 1 over 3 to the n plus 1 power. And distribute that through the numerator and denominator of this fraction. And we don't really need the absolute values because everything is positive. So we have 7 times the limit as n approaches infinity. And we have 3 to the n over 3 to the n plus 1 plus 1 over 3 to the n plus 1. And then in the denominator, we've got 3 to the n plus 1 divided by 3 to the n plus 1 is 1, plus 1 over 3 to the n plus 1.
Trying to rap or something.
And we have n bases of 3 in the numerator, and we have one more base of 3 in this denominator. And what do we have here? As we let n approach infinity with the 7 out front, we have the limit as n approaches infinity. What's our first term? 1/3. Plus, what's 1 over 3 to infinity approaching? 0 over 1 plus 1 over something approaching infinity is approaching 0. And our final answer is 7/3, which is greater than 1. So therefore, by the ratio test, the given series diverges. Okay. Bam! We got some time left. All right. One more example. Whoop, whoop. What?
Do you think AP, like, will we need to do that whole proof thing with the 1 all over the 3n plus 1? I just, like, canceled it out at the first step.
Canceled it out. Oh, you looked at the 3 to the n power and the 3 to the n plus 1, and you knew the plus 1 wasn't going to really do anything.
Yeah.
These questions tend to be really like a lot of stuff involved if they're a free response question. So I would say you could probably get away with that. And you might have questions like this that are multiple choice. But I don't believe you're going to get a free response question that is just here is a series, determine if it converges or diverges. All right, let's take a look at one more. So we have the summation where n starts at 1 and goes to infinity of n factorial over 2 times 4 times 6 times ... times 2 to the first. We do have a what in this a sub n term? A factorial, which opens up the door for a ratio test to be a good test. And certainly, how are we going to like integrate this, right? There's no like even function value for the denominator right now. So we're going to do the limit as n approaches infinity of the absolute value, even though this is always going to be positive, so I'll drop that in the next one. A sub n plus 1, so we have n plus 1 factorial over 2 times 4 times 6 times ... times 2 to the n plus 1. Make sure you're taking out the n and substituting n plus 1. Don't write 2n plus 1, like it's 2 times n plus 1. So here's a sub n, and we're going to divide by a sub n. Oh, excuse me, this is a sub n plus 1, and we're going to divide by a sub n, which instead of showing the division of a sub n, I'm going to show the multiplication of the reciprocal. So we're going to be multiplying that by the reciprocal of our original a sub n. So 2 times 4 times 6 times ... 2n over n factorial. Now what's going to cancel? The expansion of n plus 1 factorial is n plus 1 times n factorial. So the n factorials are going to cancel. And what else is going to cancel? This is 2 times 4 times 6 times ... times 2n times the next number in this list is going to be 2n plus 2. So the 2 times 4 times 6 all the way up to 2n are going to cancel. All those common factors are going to cancel. So we end up with a limit as n approaches infinity of the absolute value of what do we have left? N plus 1 over 2n plus 2. So this looked really, really complicated with that expansion of the factors in the denominator. But with a ratio test, we're already at the limit as n approaches infinity of a sub n plus 1 divided by a sub n comes out to be 1/2, with the numerator of this polynomial being 1 and the denominator power or degree being 1. We can just look at those leading coefficients and say our answer is 1/2, which is what? Which is less than 1. So therefore, by the ratio test, the given series converges. Bam! Go do your homework. Absolutely. The a sub n term doesn't alternate to be positive or negative, so I'm going to leave off the absolute idea. Woo! Dang, just finished. All right, have a good one.